All right, picking right up with our terms, just flicking back, we have specific humidity, saturation specific humidity. We just looked at those on the curve. Specific humidity is the amount of water present. Saturation specific humidity is the amount of water that would be present if I was at 100% saturation, or if evaporation and condensation are in equilibrium, so they're both doing 50-50. Or another way to think of it is if evaporation was to happen, condensation would occur immediately, right? So water would come out of suspension immediately. Another set of terms that you'll see is mixing ratio and saturation mixing ratio. Now, right here it says similar to. It's not similar to, it is the same thing. They are similar in the sense that mixing ratio is specifically referring to the units of gas per kilogram. So it's a gram per kilogram in my gaseous form. And saturation mixing ratio is my grams per kilogram at that. But it's referring to, once again, the same things as specific humidity. Mixing ratio is specific humidity. It's the amount of water currently present as a measurement just in grams per kilogram. And mixing ratio or saturation mixing ratio is saturation specific humidity. Same thing, it's just in the units of grams per kilogram. So it's not in grams per meter cubed, which is what specific humidity is in. So that's the only difference in the term. Otherwise, they're referring to the same thing. So yes, just keeping our terms straight. The next term is relative humidity. Relative humidity is a percentage, and what it is it's the percentage to the line that is 100%. It's the percentage to that 100% specific humidity. So if I say that my relative humidity today is 50%, I am saying that I am 50% of the way to 100%. That's what we're saying. So it's just a percentage or ratio based on the numbers found, based on that line curve that we were just looking at. Relative humidity is one of the things that we see all the time when we're looking at weather reports. And what they're telling you is the percentage to 100% saturation. So they're telling you how far away you are to getting to 100%. And at 100%, that could mean precipitation. That could mean cloud forming on the ground, so fogginess, and it could just mean a whole lot of humidity on the surface if I'm approaching that 100%, but I'm not quite reaching that 100%, right? So I'm just right there, so that's what we call an extremely humid day. One of the things to keep in mind with relative humidity is that if the temperature is cooler, it requires less water present to reach saturation, because there's less space between air molecules. So I have less space to actually fit the water that I'm trying to fit into the atmosphere. Where if it's a warmer day, it requires more water to get to that same. So 50% relative humidity on a day that's cold, on a day that's near freezing, doesn't require as much moisture in the atmosphere as 50% relative humidity on a day that's very, very hot. On those days, 50% relative humidity is downright sticky. So the amount of moisture present can actually be different. Or another way to say it is the amount of mixing ratio, right? Or the amount of specific humidity, the exact amount of water present, would be different if the temperature is cold than if the temperature is warm, even if relative humidity is telling me they are both at 50%. Another key relationship to keep in mind, and that's what this slide is showing, is that throughout the day, temperature changes. And so the relationship of relative humidity will change based on that fluctuation of temperature. So during the morning, for example, it's cooler, and I have a certain amount of water present, right? And so those two things might not meet. And so in the morning, I might be at a relative humidity reading of only about, well, for example, here, they have a relative humidity reading around 60%, right? But during the day, the temperature gets warmer, so there's more space for more water. And at that point, my relative humidity percentage goes all the way down to like 25, 30 on my line here, right? So then I start increasing the amount of evaporation taking place, and so the amount of water is getting increased meaning that I'm rising, but temperature begins to drop. And so I meet back at a relative humidity around 50%, right? And this continues throughout the day. And so these two things are constantly in flux, or my percentage, my relative humidity percentage that I'm reading off to you is constantly fluctuating based on the amount of moisture present and the temperature with which it is throughout the day, right? These are direct relationships. Dew point. Dew point is the temperature with which, if I was to cool off the temperature, make it colder, but not change the amount of moisture present, it's the temperature that if it got to that cooler temperature, I would have 100% relative humidity. It's the point of saturation specific humidity or saturation mixing ratio, right? I will hit that line on that curve we looked at the first video. Frost point is the temperature with which I will reach that line, but I will see an action of solids happening as opposed to liquids. So dew point is the temperature that I would hit to get liquid water. Frost point is the temperature that I get to hit solid water, right? Dew point, frost point, just showing you the two. I'm going to go into this on slides on the curve, and I'll just do a little video. You'll just see it whiteboard style with the slide on the curve. The tool that we use to measure our dew point and the tool that we use to measure our temperature is a sling psychrometer. It's this little double thermostat setup. Yeah, here we go. And one has a wet bulb, and that's a little sheet that goes on top that we actually wet with water. And the other one is the dry bulb, and then we swing it around. And actually, if you had a lab on campus, this is my favorite lab of them all because you swing it around and inevitably somebody hits themselves in the head. So I just do this like watch you all very intently, all wide-eyed, waiting for somebody to, hit themselves in the head. Student will come up, be like, I have a question. I'll be like, quiet, I'm watching. Because it's like my moment. I don't know why I enjoy it so much. Secretly evil, secretly evil. So here we go. Our wet bulb is the dew point temperature. It's telling me the saturation level because the more water that is removed or the cooler the temperature gets on my wet bulb thermometer, the more difference or the more space there is for water in the atmosphere. So the bigger the gap between the two temperatures, for example, if this one happens to be 20 degrees and this one happens to be 15 degrees, that has a 5-degree difference in temperature. On the other hand, if I read this and this was 30 degrees and this is 20 degrees, so that's a 10-degree difference in temperature, the one with the 10-degree difference in temperature has a lower relative humidity percentage and there's more space for more water. On the other hand, the one with the 5-degree temperature has a higher relative humidity percentage and has less space, can't hold as much water as the one that has the 10-degree difference gap. So that difference in temperature gives me an exorbitant amount of information about what's going on in the atmosphere. And that can come from just swinging around this little sling psychrometer with the double bulbs, one being the wet bulb and one being a dry bulb. Water vapor and distribution over the surface of the earth changes based on multiple different attributes. One of them is location. Am I coastal or am I inland? Inland regions have a harder time receiving moisture. Think of inland deserts, right? There's also a difference in our latitudes. So our latitude location also determines what's going to happen with water or moisture on the Earth's surface. Am I under a location of high pressure or am I under a location of low pressure? Remember, if I'm under high pressure, all the air molecules are leaving my location. They ain't hanging out with me. They're going up and leaving, right? So those locations have sunny, clear skies, but it's also very dry. Where if I'm under low pressure, I'm seeing water fall through the atmosphere, drop down towards the surface of the earth. And as it's doing that, it's condensing and making the gas molecules are turning into clouds, and I'm having cloudy days, but moisture collection, right? So it does matter my location on the surface. All of this goes back to my saturation curve. I will do a video on this, and I'm going to just go through these terms in one last video, and then I will do my curve math, show you how to use the curve video.